In this video, we're going to solve a stoichiometry problem that is asking us to find out how many grams of a product can be formed when we know the grams of a particular reactant that are being used. Now, you may recognize this as a combustion reaction. We have a hydrocarbon that is reacting with oxygen, and the products are carbon dioxide and water. That is a very classic pattern for a combustion reaction. And keep in mind that in a combustion, the only thing that's going to change is the identity of the hydrocarbon. You will always need oxygen to get the reaction to occur, and the products will always be CO2 and water. That is not going to change. Now, the first thing we have to do before we do any of this stoichiometry is make sure that this reaction is balanced. And just at first glance, we can see that it isn't, because on the left-hand side, we have 2 carbons, and on the right-hand side, we have 1 carbon. So I'm going to fix that by multiplying CO2 by 2 to account for the carbons on the left side of the equation. Now, on the right-hand side, always start with carbon when you're balancing combustion reactions, then move on to hydrogen. And I see on the left I have 2 hydrogens, on the right I have 2 hydrogens. So hydrogens right now are good to go. The last element you want to balance is oxygen, and that's because in combustion reactions it appears in 2 formulas and it tends to complicate things a bit. So in CO2, we're multiplying the subscript 2 of oxygen by the coefficient 2, which means we have 4 oxygens. In water, there's only 1 oxygen. Now, when we add these up, it means we have 5 oxygens on the right side of the equation, but 2 on the left. And this is the traditionally tricky part of combustion reactions because you now have an odd number of oxygens on the right and an even number of oxygens on the left. So the way that we can fix that is by using a fractional coefficient. If I want to turn 2 into 5, I can multiply it by 5 halves, because the 2 in the subscript is going to cancel out the 2 in the denominator, which leaves you with 5 oxygens. So that's something you can put in its place to just make the balancing a little bit easier. Now, we can't leave the reaction the way that currently is, because 5 halves of an oxygen molecule doesn't really make sense. We can't have half of a molecule. So to get rid of that fraction, I'm going to multiply the entire equation by 2, which means that every coefficient in that equation is getting multiplied by 2. And in front of water and C2H2, since there wasn't anything in its place, there's really a coefficient of 1 that we're just not bothering to draw in. So I'm going to multiply everything by 2, which means we have 2 C2H2 plus 5 oxygen molecules plus 4 CO2 molecules and 2 water molecules. And now our reaction is balanced, and you can always go back and check that that is the case. So now that we have a balanced chemical equation, we can turn to our problem. It's telling us that we have 35 grams of C2H2, so that is given. And it's asking us to solve for grams of carbon dioxide that are being produced. Now, we don't have a direct conversion from grams of C2H2 to grams of carbon dioxide because those have different masses. But we can establish a molar relationship between those compounds by looking at the coefficients in the balanced chemical equation. And since this problem is not specifying the amount of oxygen that's present, we're assuming that we have an excess of oxygen that allows this reaction to go to completion. So looking at the coefficients in the formula, it's telling us that for every 4 moles of carbon dioxide that are produced, we need 2 moles of C2H2 present. So now we have a molar relationship that will take us from moles of C2H2 to moles of CO2. But what we're really interested in is grams of CO2. Well, once you know the moles of CO2, you can get to grams of CO2 using its molar mass. And we are given 35 grams of C2H2 present in this reaction. Well, if we know the mass of that compound, we can get to moles of the compound using its molar mass. which means that we're going to need to calculate the molar masses of each of these compounds. For that, we will need the periodic table. And in 1 mole of carbon, we have 12.011 grams. In 1 mole of hydrogen, that will weigh 1.01 grams. Now, I do need to account for the amounts of each one in the formula. And we have 2 moles of carbon, so I will multiply that by 2. And 2 moles of hydrogen, so I will multiply that by 2. And now we can add those values together to get the total. So 1 mole of C2H2 will have a mass of 26.042 grams. And we'll do the exact same thing for CO2. And 1 mole of oxygen is about 16 grams. But keep in mind that we have 2 oxygens in the formula, so we need to multiply that by 2. And I'm just going to add the mass of carbon because there's only 1 of them in the formula. So it will be pretty straightforward. So 1 mole of CO2 will have a mass of 44.01 grams. And now that we have all of the information we need, we can do that conversion. I always start with what is given to us, so I'm going to start with 35 grams of C2H2. And whatever unit is up top that we're trying to get rid of, that's the unit that's going to have to go on the bottom. So I want to put grams of C2H2 on the bottom, and I get that value from the molar mass. So this is telling me that in 1 mole of C2H2, we have 26.042 grams of C2H2. And now the grams of C2H2 cancel out, and we're looking at moles of C2H2. Now I'm not interested in C2H2, I'm interested in grams of carbon dioxide. So I need to put the moles of C2H2 in the denominator to get those to cancel, and I'm going to use the molar relationship that we established from the coefficients in the chemical equation. Well, for every 2 moles of C2H2, we are producing 4 moles of carbon dioxide. And now the moles of C2H2 cancel out, and we have moles of carbon dioxide. Finally, when we have moles of carbon dioxide, we can convert that to the mass using the molar mass of that compound. So whatever unit is up top here, that's the unit that has to be on the bottom for it to cancel out, which means 1 mole of CO2 will be on the bottom, and 44.011 grams of CO2 will be up top. And then the moles of CO2 cancel. So now everything up top gets multiplied and gets divided by everything on the bottom. So we're going to plug that in and get our final answer. Okay, I'm getting 118.3, and I should round that to the appropriate number of sig figs. And it looks like we started with 3 sig figs in the equation. We did a bunch of multiplication and division, so we're going by the lowest number of sig figs, and that'll round to 118 grams of carbon dioxide.